Hello, Assalamualaikum and a very good day to all students. So the topic of our lecture today is friction and uniform flow in open channel. So first, I will introduce the concept of friction, and second, we will see together how Chassis equation is derived, and we can compare it with Manning's equation. So all these notes are taken from the textbook that I've shared with you before. Okay, previously we learned about energy equation in open channel flow. Okay, if you notice, this energy equation deals with the perspective of frictionless in horizontal channel. I repeat, frictionless, tiada geseran. Okay, in this lecture, however, we will relax the assumption of frictionless, meaning we will now consider the friction. Okay. Oh, by the way, I just want you to imagine if you can think of any channel without friction. Maybe you can think of something. Yeah, is there any open channel without friction? Okay, by the way, in today's lecture, we will explore two commonly used friction equations, which is Chassis equation and also Manning's equation. Okay. Okay, can you imagine of friction? Can you imagine what friction is? Okay, if you think of an example in river, for example. So the friction comes from the grass at the banks of the river. Okay? Boleh imagine tak? And also from the bottom, there must be like some sediments or stones. That is where the friction comes from. Okay? Okay, first let's look at in uniform flow. So uniform flow is a flow that is unchanging. Okay, so in uniform flow, you will not observe the change in depth, which is why you have um, this dy over dx, which is 0. Okay, which means the depth does not change along the direction of flow in the open channel. Okay. And other characteristics affecting flow in open channel, example discharge, roughness, channel size and shape, and channel slope, will also do not change in uniform flow. Okay, since depth is not changing, energy must also be constant. Okay, so dE over dx is equals to 0. Okay, okay, bear in mind, uniform flow is a concept. It is an idealization because in reality, channel geometry, slope, sediment size, and vegetation are changing constantly. Okay. Okay, this is taken from the textbook in figure 4.1. Okay, so this is an example. So if there is a lake here and the water flow from the lake into this channel. So somewhere here in the middle, there is an area which you could get uniform flow. Okay, so obviously this must have, this area, the depth will not change in the direction of the flow. So there can be uniform flow. So maybe you can see a type of canal like this, where it is very uniform. Maybe we could get uniform flow in this kind of irrigation or whatever type of canal. Okay, so by the way, this is Panama Canal. This is taken from this website. Okay, all right. Okay, why does uniform flow occur? Okay, because there is dynamic equilibrium between forces is realized in the channel. Okay, so driving force, in this case, is gravity, is balanced by the resisting force, which is friction. So when this is balanced, then we can get uniform flow. Okay, I think you must be familiar with this figure. This is an object falling down. So when it the object is falling down with velocity at t, okay? So this object has gravity force acting on it, which is Fg is equal to mg. This is the weight, okay? But on the other hand, there is also drag force going to the opposite direction, okay? So when the equilibrium is achieved, then the velocity of the object is called as having terminal velocity. Okay, maybe you have been exposed to this terminal velocity before, right? So in the case of uniform flow in open channel, so the situation is like this. Okay, first we have, you know that the water flows longitudinal from the upstream to the downstream. Okay, so then this flow, this channel, it has a certain slope, which is theta. Yeah, this slope. So as the water flow in this direction, it has its v, the velocity. Okay. And for this section, if we examine this section, so you can see um, the difference of x. I mean the distance from point 1 to point 2. Okay. So this is the distance. Okay. In this case, the gravity force is the longitudinal force moving into this direction to the right. Okay. Can you see this? Okay, so this is the gravity force in this case. Okay, again. Okay, so the gravity force in this case is Fg, this one. Oh. Okay, again. Okay, so this gravity force is moving into this direction. See here. Okay, so this is theta. Okay, so this is actually the weight. The weight of the flow of the water. Okay, because it's like this, but since this is an object, so the weight is m mass times by gravity. But in this case, since we have a slope here, okay, and we have a slope here, so this is then our Fg is equals to this formula. Okay. Okay, so this is unit weight, and this is A times distance, so this is volume. Okay, so we multiply by sine theta. Okay, and at the same time we have drag force, so drag force is according to this equation. Okay, so this is shear force. Okay, shear force we multiply by wetted parameter. This is wetted parameter, and this is also distance. Okay, so this is how it looks like. Yeah, when we have uniform flow, so the gravity force is equals to resisting force. Okay,